Let's look at limits involving infinity, and these are two different types. One is as x goes to infinity or negative infinity, and the other is a limit where the answer is infinity. So one thing to know about limits as x goes to infinity or negative infinity, we're talking about the end behavior. We're talking about the extreme left end and the extreme right end. And end behavior is often characterized or described by a horizontal asymptote if one exists. So one way you can answer these is by using the rules you learned in pre-cal or algebra 2, where you can compare the degree on top and bottom. And one thing to note is that this approach is really only safe if the numerator and denominator, so I'm just going to say top and bottom to make it simpler, if the top and bottom are polynomials. So that just means they're x's to integer powers, no square roots, no e's, no sine, no trig, no exponential. So looking at these, my numerator and denominator are polynomials. And in this case, you can compare the top and the bottom degrees. And for number one, the bottom degree is larger than the top, which means the answer is 0. And so if the bottom is bigger than the top, the answer is 0. Number two, the top is bigger than the bottom. And in pre-cal, that meant that there was no horizontal asymptote. We will not worry in calculus about slant asymptotes. So we're looking strictly for horizontals. And there is no horizontal asymptote on 2 because the top is bigger than the bottom. And so technically an answer of D and E is correct. However, if there is no horizontal asymptote, then that means that as we work in this case out to the left, if there's no horizontal asymptote, we're not leveling off, which means as I go to the left, I'm either going up or I'm going down. I've got to be doing one of those two if there is no horizontal asymptote off to the left. And so what we're going to have to do is determine, is this limit or is this function going up or down, which means is the answer infinity or is the answer negative infinity? And to figure that out, what we do is we look at the high power terms in top and bottom. In this case, that is 3x to the 5th and x squared. And I just imagine, what if I plugged a negative number in for the x's there? So I'm going to plug in a negative. So I would have 3 times a negative to the 5th over a negative squared. A negative to the 5th power will remain negative. A negative squared will turn positive, and that will ultimately give you a negative result. So this thing, because my high powered terms return a negative value, that means that this limit is actually going to negative infinity. And so I prefer an answer of negative infinity in this case. So D and E is not wrong, but we could be a little bit more specific. So let's look at number 3. And number 3 is when the degrees are equal. I have an x cubed and I have an x squared. And if the degrees are equal, you divide the coefficients. So y'all may remember those 3 rules from pre-cal. And you may have even seen them in algebra 2. I'm not 100% sure of that. We divide the coefficients there. So if the bottom degree is bigger, answer is 0. Top degree bigger, one of the two infinities. I want you to figure that out. And if the degrees are equal, you divide the coefficients of the high power terms. And remember, these rules are only if x is going to infinity or negative infinity. If x is approaching a number, then these rules do not work. So don't accidentally try these degree rules if it's not approaching infinity. Okay. Another way to do this, and this is the more mathy way of doing it, I call the Math League of America, which really doesn't exist. I just made that up. But the true math way of answering these, and it takes more time, but it's a little bit safer. What we'll do is we look in the denominator. First, x is going to infinity. Check that first. Then I'll look in the denominator, and I divide everything on top and bottom by the high power of x. In this case, that's x cubed. So I'm going to divide everything by an x cubed. Everything gets divided by an x cubed. And then I rewrite my limit, reducing each of those terms. So the limit as x goes to infinity. 3 over x cubed does not reduce. 5x cubed over x cubed is just 5. 2x cubed over x cubed is 2. 12 over x cubed is 12 over x cubed. Okay. Now what I'll do is I'll reevaluate my limit, and the limit is only going to influence the things with an x. And in this case, that will be 3 over x cubed and 12 over x cubed. And so if I were to plug infinity into that, I would have 3 divided by infinity cubed, which is huge, and any number divided by infinity will always approach 0. Same thing with 12 over infinity, that's going to approach 0. So this limit ends up approaching, or this function approaches 0 minus 5 over 2 plus 0, or negative 5 halves. The good thing about this approach, even though it takes longer, the good thing about this approach is it works for all 3 cases. You don't have to memorize what the rules mean. So if you forget what top bigger than bottom means or bottom bigger than top means, you can always use this approach. So it takes longer, but it is safer. It's a little bit more mathematical. Rote memorization, which is what we used here on the first 3, can be problematic. So if you have any doubt whatsoever, go with this approach because it will work every single time. Now, if you don't have a polynomial, so if you look at number 5, I have a denominator with a square root. If you don't have polynomials in numerator and denominator, I strongly recommend you do that longer approach. So what I'm going to do is I'm going to look in the denominator, and I want to find the highest power of x in the denominator, and I see an x squared. However, notice that x squared is under a square root. So it's really the square root of x squared in the denominator, which is the same thing as an x. So I'm going to divide everything by x to the first. So in the numerator, going to be pretty easy. 2 divided by x divided by x. In the denominator, I want what I divide by to resemble the structure of the denominator. So instead of dividing by an x, I'm going to divide the whole thing by the square root of x squared. I'm still dividing by x to the first, but it's just presented in a way that looks the same as my denominator. So now I'm going to clean this up. Limit, x goes to infinity. The top is easy. X over x is 1. 2 over x does not reduce. The denominator, I'm going to write as 1 big square root. And I have 9x squared over x squared, which is just 9. And 1 over x squared will not reduce. So there's how we're going to handle square roots. And I strongly recommend you use the division trick and not try to memorize or use the degree on top and bottom rules. So now that I have reduced this, I'll look at my terms that have an x in them. Both of them is a number over infinity. 2, when I plug in infinity for x, 2 over infinity will approach 0. 1 over infinity squared will also approach 0. And my answer is 1 over the square root of 9. And if you're really smart, you might know that the square root of 9 is 3. So there's our answer for 5. And getting a little bit tricky, here it's approaching infinity. I do have square roots. However, I do not have a fraction. And that's really a problem. When you're doing limits as x is going to infinity or negative infinity, you really want a fraction with variables on top and bottom. And if you look at every problem we've done so far, we have had fractions with variables in the denominator. That's really the key. You want variables in the denominator. So I'm going to force that to happen here by multiplying by the conjugate of the numerator. So I'm going to multiply top and bottom by root 9x squared plus x plus 3x. So there's the conjugate. The denominator, same thing. Then we will expand the numerator. Those are my conjugates, so I'm going to expand the numerator. So limit x goes to infinity. Root stuff times root stuff is the stuff. So we have 9x squared plus x. Negative 3x times positive 3x is negative 9x squared all over. Then I have the square root. 9x squared plus x plus 3x. My 9x squared subtract and go away in the numerator. Now I'm going to do my division trick. I have a fraction. I have variables in the denominator. That's what I wanted. Now I want to look in my denominator and find the highest power of x. So I see x to the first. Here's an x to the first. There's an x squared, but again, that is under a square root. So the square root of x squared is x to the first. I'm going to divide everything by an x to the first. But the square root part, I want to divide that by the square root of x squared. I want what I divide by to resemble what it's dividing into. And so I use square root of x squared right there. Let's clean those fractions up. Limit as x goes to infinity. X over x is 1 divided by 3x over x is 3 over here for the square root. I'm going to do one big square root. 9x squared over x squared is 9. 1x over x squared is 1 over x. And now there is a single x remaining that the limit will influence. So if I plug in infinity, 1 divided by infinity does approach 0. And so I'm left with an answer of 1 over square root 9 plus 3, or 1/6. So there's the answer for that one. So we're stepping up difficulty probably quite a bit because we had to use conjugates. You really need variables in the denominator if x is approaching infinity. So we forced the issue by using the conjugate here. Okay, one more as x is going to an infinity. And in this case, we're going to negative infinity. That's important. Already have variables on top and bottom, particularly the bottom is what I care about. So I have x is in the denominator. So I'm going to divide by my high power of x because I am going to infinity. I see the square root. I'm not going to try to use a memorized degree rule. So I'm going to divide. Let's see, I have an x to the first. I have the square root of x squared, but that again is just x to the first. So I'm going to divide everything by an x, by an x, by an x. Now the square root, we're going to do something different this time because x is going to negative infinity. Let's think about x is going to negative infinity. That means my x's are negative. I'm working my way out to the left with negative x's. The reason we were dividing by the square root of x squared earlier is because if I want an x to the first, the square root of x squared does equal x, right? But the problem here is that my x's are negative. If x's are positive, that rule works out just fine. So if x is greater than 0, yeah, the square root of x squared does equal x. And if you wanted to test that, we could plug in, I don't know, let's test x equals 4. So if I plug in 4 for my x's, so I have 4 squared, I'm going to plug in 4 for this x. I have the square root, and the square root of 4 squared would be the square root of 16. That is 4. That checks out. However, if you test a negative value for x, if x was negative 4, and I plugged negative 4 in for my x's, so I have a negative 4 squared on the right side, I would have a negative 4. If you work that out, we end up with, whoops, I don't need a square root over there. Undo. There, of course it did all that. So I have negative 4 squared in for this x, and then I have a negative 4 in for the x on the right side. When you square root negative 4 squared, that turns into the square root of 16, and the square root of 16 does not equal negative 4. That's a false statement. That's an issue. So when x's are negative, I'll go blue. So if x is less than 0, which is what we have here, the square root of x squared no longer equals x. So what we have to do is we have to divide by the negative square root of x squared. So we're going to use a negative square root of x squared because if you introduce that negative on the right side, now this equation holds true. I end up with negative 4 does equal negative 4, and it works. So when x is going to negative infinity and you're dividing by a square root of x squared, you have to remember that that needs to be negative because of the negative x's. We have to preserve that negative property of x. And that's the only tricky part that makes this different than going to positive infinity. Everything else is going to work out the same. So if x goes to negative infinity, the numerator will simplify to 2 minus 3 over x. The denominator, 6x over x is 6. That's the easy part. Now for the big square root, I have a negative in the denominator, so I'm going to put that negative out here. 16x squared over x squared is 16. 2x over x squared is 2 over x. And as x goes to infinity, a number over infinity will approach 0. So those are each approaching 0, which gives me 2 minus 0 over the negative square root of 16 plus 0 plus 6. That ends up being 2 over negative 4 plus 6 is 2, which gives you an answer of 1. So do remember that for negative x's, if we are going to negative infinity and you have to use the square root of x squared, you actually need to use the negative square root of x squared for those negative x's. All right, 2 more, and these are a lot quicker. These are limits where infinity or negative infinity ends up being the answer, and you notice x is approaching a constant. If x is approaching a constant, your first step is always to plug that constant in and see what happens. So when I plug in 3, I'm going to have 5 divided by 0, and that's an issue. It's not indeterminate. Indeterminate is 0 over 0, and that would mean we factor and cancel or do something of that nature. This time, if you have a 0 in the denominator, a number over 0, and I should say a non-zero number over 0, that means there is a vertical asymptote. We are looking at a vertical asymptote here. And let's think about a vertical asymptote. So what I know about this function is at x equals 3, I have a vertical asymptote. So here's my 3. And if you think about a vertical asymptote, I'm only worried about the left side. As you approach a vertical asymptote, your function is either going to be going up or going down. It's got to be doing one of those two. And so this means that since this is a one-sided limit, we're not looking at both sides, this answer will be either infinity if the function is going up, or if the function is going down on the left side of that asymptote, it's negative infinity. So we need to determine what is the behavior at that asymptote. And the way I do that, and there may be other methods, but what I do, all we have to do is determine if we have a positive or a negative value. So I'm going to test a value of x very close to the asymptote. You may be thinking 2 is on the left side of 3 and it's close. Kind of, yes, but in the world of limits, if you go all the way to the next integer, that could be a problem. So we're actually going to test really close to 3. I'm going to go all the way to 2.9. And if I plug in 2.9, I'll have 5 in the numerator. My denominator is 2.9 minus 3. And what I end up with is a positive numerator of 5. I have a negative denominator. That will end up being a negative result. Therefore, I know that the answer to this limit, x approaches 3 from the left, 5 over x minus 3, is going to approach negative infinity, because when I tested a value just to the left of the asymptote, I ended up getting a negative result. So I know we're looking at this, not that. One more. Okay, so here limit is x approaches 5 of this function. So let's see, if I plug in 5, remember we're approaching a number. If I plug in 5, I have 5 over 0 squared. So again, that means there's a vertical asymptote. There's a vertical asymptote at x equals 5. And if we think about that vertical asymptote, so I'm going to go over and I'm going to sketch this just to give me a visualization here. There's my vertical asymptote at 5. This problem, however, doesn't specify left or right. It's looking at both sides. So we actually need to consider the left and the right. And at a vertical asymptote, we could have a lot of different behaviors. I could have the left side going up. I could have the right side going up. And if both left and right are going up, then the answer would be positive infinity. If left and right are going down, if they're both going down on each side, then the answer would be negative infinity. But there is also the option that one side is going down and the other side is going up. And in that case, the answer does not exist. Both sides are not going to the same place. So we have 3 options on this one because we are considering both sides. It's either infinity, negative infinity, or does not exist. And we figure that out similarly to how we did the last problem. I'm going to test values just to the left and right of x equals 5. So I'm going to test 4.9. That's my left side, so I've got to look at the left. And if I plug in 4.9, I have 4.9 on top. That's positive. And if I plug 4.9 into the bottom, I have 4.9 minus 5, but I'm squaring it. That would also be positive. So I have a positive over a positive. That means my left side is going to positive infinity. So right now, I'm going to go back over here and adjust my drawing here. I know that my left side is going up. Now I'm going to test the right side. So I'm going to test something just barely to the right of 5. So let's try x equals 5.1. And if I do that, I have 5.1 in the numerator. On the bottom, 5.1 minus 5. That's positive, but it really doesn't matter because I'm squaring the denominator anyway. My denominator will always be positive unless I plug in 5. So if on the right side of 5, I ended up with 2 positives. That means my right side is also going up. And since I have tested both sides and I know that they're both going to positive infinity, I can now say that the limit as x goes to 5 of x over x minus 5 squared is positive infinity, because both sides were going to positive infinity. If they were going to different infinities, one going up, one going down, then the answer to 9 would have been does not exist. But we did show that both sides were going to positive infinity. So there is your answer.